Thanks for coming. This is part of our search for a computational neuroscience position. This is Ben Huh. When Peter Diane was, I told him about this, recommended me all over the world. I kept calling you Ben Huh. But I couldn't, you talk so fast.
Yeah.
Okay, so it's thanks for coming. This is part of our search for a computational neuroscience at MIT. Ben discussed it's not fair to say that he just when Peter Diane was, I told him about switch from biology to physics. I kept calling you Ben Huh. But I couldn't, talk so fast.
Yeah.
Okay, so thanks anyway. From there, you have again part of our search for computational neuroscience at MIT, London. Then you spent extended group there. It's not fair to say that he just when Peter Diane was, I told him about from biology early on in his career to physics. I kept calling him Ben Huh. But I couldn't, talk so fast.
Yeah. Well, thanks so much for the invitation. Great pleasure to see you. And this start with a little bit of background. So I'm generally interested in how functionality arises in dynamical systems and try to understand it from the perspective of the principle of optimality. The optimality principle provides a great theoretical framework, especially for biological. Thanks so much for the invitation. So, for example, in my previous work, I worked on studied a phenomenon known as one-third power law, and between the speed and curvature of curved handles. So for example, I'm generally interested in how functionality arises in dynamical systems and try to understand it from the perspective of the principle of optimality. The optimality principle provides a great theoretical framework, especially for biological. Thanks so much for the invitation. For example, I worked on studied a phenomenon known as one-third power law. And this is very interesting. So I was interested in how the speed and curvature of static curvature comes about. For example, I'm generally interested in how functionality of fundamental control theory. And so long story short, it turns out, let's see. Oh, yes, other movement too. Computer's a bit slow today. So, long story short, the optical control theory predicts this one-third power law, so that's the number here, for elliptic movement, but it also predicts other power laws depending on the shape. So it goes all the way from 2/3 to 0. So here x-axis is interpreting the biological data. So all along before too. And if you look at people's data, there was different power laws for different shapes. But then without knowing which feature to look for example, here how to categorize the curved shapes, all this variation just becomes meaningless noise. And of course, if you then average out this effect, then you get back to the just one-third power law, which is precisely interpreting the biological for dealing with real-time sensory motor processing, some thinking and decision-making in the middle. And yeah, so here's the example. So if you look at this, this moving image, you can easily see what's written here. There's a motion scientist. But as soon as you stop the motion, and you can't really see what's going on there. But anyway, so this is an interesting example. So before going further, it's one thing we need to clarify. So does spike represent a binary signal, or is it a real number? Some thinking and decision making in the middle. So I think there's a lot of debate on this. And the answer is it depends how you think about spike, how you use it. So one way to look at it, if you look at the amplitude of spike, and of course it's the discrete signal, right? 0 or 1. And so if you think about in terms of rate, if you want to represent a real number in terms of the average number of spikes, then you take many spikes to approximate a real number. So in that sense, I think a spike is kind of inferior. It depends how you think about spike, how you use a number. So, but then if you look at, there's another feature of spike, which is the timing of when the spike happens, right? And of course, that time is a real number. So if you can make use of the spike time to represent some temporal information of your signal, then this can give you a lot more efficient way to represent the information. So these two ways of viewing it, spike is related to how we do the real sampling. In that sense, sampling is you do sampling only when the signal passes through this threshold, right? So and so for example, here when the signal is not changing much, you can skip this whole time frame. But then when it's changing fast, you can get lots of samples. So this is the event-driven way of doing sampling versus the clock-driven. So here now, the signal amplitude is now discretized, but then the time is continuous. Okay. The sampling is, and how does it actually work? So yeah, so here again, you do sampling only when changing is going through this threshold, and when it's going down, in fact here is making negative spikes, and when it's going, and so for here when the signal is not changing much, you can skip this whole. And so if you want to understand what kind of computation might be going on in the brain, we need to a more efficient way to explore the whole space of this general spike-based computations. So here are some examples showing how the rate-based method cannot be really useful for decoding, for understanding. So this is what happens when you touch your clothing and move your finger across of the texture. Then the mechanosensory neuron will generate spikes and converts the texture information into this spatial-temporal pattern of spikes. And you can tell the difference between textures from this spatial-temporal patterns. And so for some clothing, so nylon, you get very regular pattern, so there's not much variation between the timing gap between spikes. For others, there's a lot more variability. And you can notice that overall firing rate is more or less the same between these textures. So you can't get the information just from that. So the crucial information is contained in the precise timing and the variation in this spike times. And it turns out the maximum resolution for this information is on the order of 2 milliseconds. So that's how much the brain can decode. But we don't know yet exactly how this decoding is done from this pattern. And here's at the end of on the output side of the brain, on the motor control. So here I'm plotting the contraction of the muscle tension over time, and in response to when you're giving this spikes. And you can see when the spike time suddenly changes, there's a small gap here, then it results in a sudden jump in the muscle tension. And here's some other examples. So when you miss the spike, so when there's larger gap, you also see this drop, largest drop. So muscle output is not just a linear. It doesn't just depend on the linear rate of the spikes, but it reacts quite non-linearly, and it cares a lot about precise spike timing. So if muscle cares about the timing of spikes, then the brain has to figure out how to come up with a fine control of spike timing. And of course, there's some also evidence from the cortical circuitry. So when the thalamic input comes into a cortical pyramidal cell, this connection, there are two inputs, one direct excitation from PC to PC, but it also goes through another step through this inhibitory interneuron. And this has the effect of this pyramidal cell receiving a positive excitatory current, followed by inhibitory current one or a few milliseconds later. And this has the effect of sharpening the integrated time window of this pyramidal cell. So this is evidence that this cortical circuitry has some built-in mechanism to manipulate spike times in millisecond resolution. And of course, and there's whole other circuitry which we have no idea exactly what's going on. But it's possible that this whole system was involved to deal with spike times in precise manner. And of course, there is an example from auditory system where this neurons here uses a precise time delay of spikes coming from 2 ears, and compare that delay to precisely figure out where the sound came from, the sound localization problem. And it is sensitive to in the order of microsecond resolution. And of course, the cellular mechanism of learning depends on spike time as well. So the difference between the input spikes and output spikes. Okay? So this is a well-known curve. So it's called the spike time-dependent plasticity. And of course, there are more examples of where precise spike times are observed in early visual system or in the songbird auditory system. And there's also phase coding in hippocampus and in relation to the phase of data oscillations there. Right? And none of these phenomena can be appropriately described just by using rate. We need a way to model spike-dependent processes in the brain. So, some water. So we need to build a model which actively make use of spikes for computation. So there'll be a spiking neural network models. And yes, and there are a few methods that's been introduced over the time. And here's a list of what's out there. So first, there are a lot of research done in random networks. So, and these models are more focused on analyzing what happens to the dynamics of the entire network when you connect a bunch of spiking neurons. And they're not necessarily interested in what kind of computation you can do. So here's an example from human brain projects where you develop very highly detailed biophysical models of the neurons and connect them in randomly and see what happens. But these models these are highly bottom-up approach, and they don't really account for the computational aspect of the circuit, though. And here's a little bit related model. So here again, you build a large-scale random network of spiking neurons. But then the idea here is that if you make the system large enough, then by chance there will be some circuits inside the network which will develop some interesting dynamics, which could be useful for some tasks. Okay. So there are, and this is, so here you don't have to train this internal this random matrix, but just to read out. So if you have some answer already built in there by chance, then you can just learn to figure out how to get it out from the network. And so this method turns out to work in some cases, but in fact, in principle, in practice, it's highly limited in usage. And I'll mention this later in some model. Okay. And another popular approach is to start from a rate network that we already know how to train, and so it's already performing some function. Then convert that rate network into spiking neurons. And so there are several methods on this too, but they're all similar in principle. So basically, you're trying to use a large number of spikes to represent a real number. And one way to do it is either to make one spiking neuron to fire with high rate, or you can replicate one rate neuron with hundreds of equivalent spiking neurons. Okay? So, but then, so you can, but in the end, even if you're dealing with spiking neurons, the whole algorithm that's running on the system is still based on rate. So there's nothing you can learn, nothing new you learn from this model. And another approach is to design the network by hand yourself. So for example, if you're interested in building a system that's selective to facial features, then you can have a neuron that does that by having it receiving input from other neurons, which are, for example, sensitive to eye shape or the mouth shape. And that can be built out of, again, features from vertical bars and horizontal bars and so on. And there are models which were built that way. But of course, this is very time-consuming. And often case, first of all, we don't even know, in many cases, which features are important. And here we know this eyes and mouth can be useful, but in most cases, we don't know which features are useful. And even if we do know the feature, we don't know how to build that out of even simpler components. And lastly, there is a brute force way of dealing with the problem. So here's an example from stomatogastric ganglion in lobster system. And it's a very small system. It can be isolated into like 3 neuron model. And these are supposed to generate this rhythmic activity that can be used in the intestines to grind food for digestion. And here there were 9 parameters. There's this connectivity between neurons and some internal parameters for each neuron. And here in this paper, they did this brute force search. So they discretized all the parameter space and searched through like over 20 million combinations of these parameters, and found that some of these parameters will give you exactly the desired patterns that we want. But of course, this kind of approach can't be really scaled up for any larger system. Actually, it goes faster than exponential. Right. So none of these methods are really useful for exploring the space of spike-based computations. So we need something a lot more efficient. And so I'm proposing to take an approach from deep learning, from AI. So there, you start with a network of neurons, and then you provide some task to perform, and you can now train the system to perform the task. So in this case, this network receives an input image on the left side, and on the right side, it's supposed to perform some classification task. So you're supposed to read out this number 60 from the image, and if you do the training, then this whole network figures out exactly which features are necessary, like some bars and edges in the lower layers, and more complex features on the higher. So you can discover the whole hierarchy of processing automatically. And the most efficient, the main tool in deep learning in this training is called the gradient descent method. So for a given task, you find the direction of updating your parameters towards to improving the performance of the network, and you take the step into the right direction. And that's a very simple idea, but it turns out it works well for all kinds of tasks. So it's a general learning rule. And the most efficient way to calculate this gradient is known as this method called backpropagation. And it's basically a chain rule from calculus. It's a chain rule going through this network, layers of network. Okay. So, but here, of course, in these deep learning models, usually what you use is rate-based neurons. So you completely get rid of the concept of time. And so this neuron will receive some static inputs, some scalar numbers, and it processes it somehow, and then it produces the output, again, the scalar analog number, which can be interpreted as the average firing rate over time. So the question is now, can we do the same thing, but without the rate neurons, but now using spiking neurons? We introduce the time and the dynamics. And it turns out, so this tool will be a great tool for our purpose, for exploring these spike-based computations. The problem is the spiking dynamics has the non-differentiability issue, which I'll talk in the next slide. And so we need a way to treat that. So, and this is exactly why nobody, even though this is a great way to method, nobody used it so far. And that's why we had all these other previous methods that I showed earlier. And in fact, I need to also worth mentioning that, in fact, this non-differentiability issue also existed in this deep learning model before too, when they first used this step function for this nonlinearity. But then later they figured out, well, if you instead use this sigmoidal function, then you can differentiate this whole thing and use the gradient descent method. So in fact, I'll be doing is essentially the same thing, the smoothing the step function to the sigmoid. So that's the whole trick. But now, this is now defined in time domain. So that's the complexity. Okay, so let me show you how to deal with this problem. So in order to build a spiking neural network, we first need to describe how the neurons interact with each other through spikes. So here's the membrane voltage of a pre-selected neuron. And when the voltage gets sufficiently depolarized, when it hits the threshold, then it will generate some spikes. And it will receive by the post-synaptic neurons in terms of this post-synaptic current. Okay? So this voltage and this current, post-synaptic currents, are now dynamically linked. And usually this linkage of dynamic the relationship is described in terms of a hard threshold. So when the voltage goes through this dotted line, that's the threshold. Then at the time of this it crosses, this will activate this post-synaptic current at the time, and then will decay over time. So here I'm describing this current as a kind of low-pass filtering of these spikes. And it can be described in terms of delta function. Here, this T star is a time of spikes, and this left side is basically just low-pass filtering. And by the way, here I'm integrating the whole area under this curve, which is basically the total charge that's been delivered by the spike. And it's normalized to be 1. And the problem of course, using hard threshold is that you either cross the threshold or not. So there's a 0, 1. There's a non-differentiability issue. So when you don't cross threshold, you get 0 charge out of it. And so that's the whole problem, non-differentiability issue. And the way to fix this is introduce soft threshold instead of hard threshold. And that can be described by defining this function I call the gate function. That's a g of voltage. And it's 0 mostly everywhere, except that it's activated near the threshold with some finite width. And this function is multiplied by v dot. That's the temporal. That's the dynamics of the preceptive voltage. So this has the effect of opening the flow of information from from voltage to the postsynaptic current only near the threshold. Okay, and yeah. So you can now see the effect of this dot threshold. So as the voltage depolarizes, you can see the current now slowly, gradually increasing, and that's in a differentiable manner. And you can, of course, compare that to Hall threshold, which is non-differentiable. And this description also has a nice property that preserves this core property of spikes, that no matter how strongly the input this preceptive neuron receives, so here I'm now changing the rate of depolarization. So sometimes it could be high or it could be a slow depolarization, but still the amount of charge delivered is always the same, okay, as long as you cross the whole threshold. And you see the same thing in the hard threshold as well. Okay. So that was hard part. So now this equation now describes how the synaptic current gets activated in a differentiable manner. And to complete the description, we also need a dynamics for the presynaptic voltage. So that's V dot. And here, for simplicity, I'll define a very simple function that depends on the voltage itself, and also J, that's the total current received by this neuron. And we can use any kind of a neuron model. It could be a simple point integram phi neuron, or it could be Hodgkin-Huxley with multiple compartmentals. But here I'm going to assume some generic form, so it can be applied to any models. Okay. Now, given these two equations, now we can build the entire network of the spiking neurons. So now the voltage and state current vectors are now the internal state variables of this network. And this network will receive some time-varying input, and it will generate some time-varying output. Okay. And there are three matrices of three parameters. So there is a W, which describes any kind of connections between these neurons. And there's a U, which maps the input current as a current into individual neurons. And this is the output mapping function. So individual neurons will receive current. That's a sum of the current coming from the other neurons. That's W times S. And here's a component coming from the external input, U times I. And the output from this network is simply the O matrix times the synaptic current, S. And now given that, and usually any kind of a supervised learning task will also have some desired target function defined over time. So now we can define the error as a difference between the actual output and the target. And then we can also define the cost function, which penalizes the error, and plus maybe some other additional penalty term for having too many spikes and so on. So now the goal of this whole system is to minimize the total cost, and we can now train the network to perform the task. Any questions so far? Okay. So now because we defined the whole network dynamics to be differentiable, now we can calculate the gradient and follow it down. And right. So the gradient for this output matrix is very simple. It's simply the error vector times the synaptic current. And we can also calculate the gradient in a similar way for other matrices. It looks a bit more complicated, but it's essentially the same idea. So it's multiplied by the whatever input for the matrix is. So for W, the input is S, so you multiply by S. For U, the input is I, so there's I term. And this whole term here has similar content as the error signal. So here, first, this term is simply the derivative of the neuron dynamics. There's nothing complicated here. But here, there's this new term called PV. And this is called the backpropagating error signal. And it's the same thing as what we had in the deep learning models. So in the end, it's a glorified chain rule. But then because now we're dealing with a dynamical system, this backpropagation rule you can also see it as a dynamical system. So that's why you have PV dot. And we also have another term for PS for each state variable, V and S. And there's this minus sign because it's going backward in time. Okay, question?
Yes, over here, I'm thinking as an experimentalist, I apologize, and I may have, as you went from current to voltage, you raised spike threshold. just help me
Sure.
understand this. Is the when I'm looking at the output there coming out of this network, is that going to be output measured in spike frequency over some time? Is that a rate coded output at this point?
Well, so it's measured in terms of, so it's a linear combination of the synaptic current coming out from other neurons. So it's postsynaptic.
So we're still at the level of the postsynaptic neuron that's integrating all this charge, and so the net result is some current at that point.
Or it could be received by the muscles as well.
Or, okay,
Right,
muscle,
yes.
but we're not yet at the super threshold thinking about the pattern or the frequency of the spikes coming out of the system there. Is that after this step?
So all the interactions between the neurons are done in terms of spikes, with filters into current. So anything that's performed by this network will be in terms of spike times. And of course, depending on what the receiving output is, maybe it's muscle or the next neuron. If it's now that there's a question whether those can how they can handle this spike output from this network.
Okay.
Yeah? Not sure if I answered it right. Yeah. Okay. Anyway, so yeah, so this is the main equation. And I just want you to notice that there is this term, the same gate function term appearing here, G of V. So in the previous equation, the forward equation, this gate function was allowing the flow of information from the voltage dynamics to postsynaptic current. Here it's going backward. It's going from the PS to PV. So I just want you to notice that this whole equation, the calculation of this gradient, now depend on the actual spike time dependence between this is the positive neuron, and then yeah. So it depends on this exact precise timing of the spikes. And this Z term has terms from the cost function, so that's the error term and the number of spikes, and all this equation goes through dynamics goes through the connectivity within the network. Okay? Anyway, so it's lots of terms here, but in the end, if you follow these equations, you get the exact gradient of the system, and you can use this to now optimize the whole network. And this was not possible until now so far. Yes.
As W gets big,
Big.
let's say the dimensions of the system, okay?
Yes.
W gets really, really large, as you might imagine happens sometimes. These correctives get small, and spread out.
What corrective?
This information that you're propagating back through gets really small, and it becomes hard to calculate.
You mean there's the gradient, the vanishing gradient problem, or?
Small. I actually have two questions, so that's
Okay.
one question. So, what do you do when W is a really large dimension? And the second thing was, in your penalty term, which was I think 2 slides ago, you squared the S as opposed to, we live in a time when L1 is the new L2.
Right.
So I was just wondering.
We could use either. I was just using it as a simple example.
Have you done that? Have you done that with
I haven't played with that yet. Yeah.
with the first question?
So first question. So of course here now the complexity of this whole calculation grows as n squared times t. So n squared is it's actually the number of synaptic connections there are in between the neurons. So but actual connectivity in the brain is quite sparse. So in fact there will be maybe coefficient alpha multiple to that too. But in the end, this is the most efficient way of it we can do it. It will have to at least grow as linearly as number of synapses. So there's nothing we can do about that. What was the other question? So right now, but there is, but we can make use of the sparsity and to make the calculation a lot more efficient.
What do you figure the sparsity is?
Where the sparsity is?
What do you estimate the brain's sparsity is?
So
You said it's quite sparse, but maybe it doesn't.
right. So I think the idea is that there are so each neurons in a cortex receive about thousands of synapses from other neurons, but then but then around the neuron, there are like way larger number of neurons there. They could potentially make the connectivity. So I thought it was like the sparsity is of 0.1% and so on. Rough estimate. Yes? Question?
I just try to understand what your meanings, and basically you try to apply the spike trains for the deep learning systems, but the spike timing is difficult to handle for adapt the deep learning system because it's a non-linear system. So that's why you try to make something the linear conversion based on the soft threshold mechanism. And then just try to calculate based on those things, and then to calculate now back propagation value.
Right.
Am I correct?
Yeah. But so yeah, of course the dynamics of the neurons is nonlinear, but also there's non-differentiability issue.
Yes,
so here
right.
I'll solve that problem.
Okay,
Yes.
I understand.
Okay, thanks. Good question. Anyway, so this is the methods that I'll be using so far. So yeah, so if there's no more questions, now I'll demonstrate how this works in some toy examples. So I'll apply these methods to train recurrent spiking networks. So by the way, so I'm not sure, maybe I haven't mentioned. So this network structure could be anything. So it could be like feed-forward structure if you want. But in general, it's most generally described in terms of recurrent connectivity. And in fact, here I'll use a fully recurrent system. And I'll train it for these 3 tasks. And they're not necessarily chosen for give us maximum information about how the brain works. But then this is just to show that it's a challenging task for this training. So it shows you how this learning works. And all of this was not possible until now. Right? So the first example I'm going to use is what's called the auto-encoding task. So the network receives some time-varying input, and here the goal is to generate output that's very close to the actual input. So it's a very simple task. And the reason why I chose this task is because there was a previous paper recently which showed how what the optimal network structure should be in terms of analytical solution. So it gives you a great sanity check whether this learning rule is actually working or not. So in this case, the network receives 2 time-varying input, and so it makes two outputs. And this is the desired output it should make. And the actual output tracks the desired one quite accurately. So the learning seems to have worked well. Here, but another challenge is so the challenge here is that the signal must be represented in the middle by using spikes. And there's also a term to penalize it, so it should use minimum number of spikes for doing that. So how does it work? So here I'm plotting the input current for one particular neuron. And here I'm plotting just the feed-forward input, so input from this input signal times u. And you can see there's a lot of fluctuation in the input. So if you simulate the neuron just with this current, then this neuron will generate lots of spikes. Okay? But here this neuron I defined 2 thresholds, both the positive and negative. So it could also make negative spikes if it gets goes negative too much. So it's just a easy choice that makes the network easier to understand, but it's not a necessary feature. The whole learning rule works for any kind of neural model. So in this case, this neuron makes 26 spikes, which is quite high. But now let's see what happens when you also include the recurrent input from other neurons. And you can see this red curve is almost the equal and opposite sign of the feed-forward input. So if you add these 2, the total current cancels out pretty much everything. So it's just there's this fluctuation around 0, and it has the effect of canceling out most of the possible spikes. So in this case, it only makes 9 spikes instead. So it dramatically decreases the number of spikes. And basically, so this recurrent interaction between neurons are acting to cancel out redundant spikes. So if one neuron already made some spike, which predicts the desired output, then it inhibits the other neuron, so it doesn't make that additional spike. So there's high degree of interaction. Oh yeah, and the W that we get from this training is close to what they found analytically, so it's minus U times O in this case. So this result shows you that this learning rule works in the level of the spike time interaction in the millisecond resolution. Yeah, right. And this canceling of redundant spikes means that this neuron is making a quite efficient way of using spikes to reconstruct the error, the signal. So the error decreases 1 over k, where k is number of spikes, instead of square root of k, which is the best you can get if you're using rate coding approach using a Postdoctoral neurons. Okay. And just to also mention what I mentioned before, so I mentioned this 2 different ways of doing sampling, either grid in the time or so vertical lines or the horizontal lines here. Here, you can think of what's happening here as a kind of generalization between these 2. So instead of vertical or horizontal, you're doing sampling using oblique lines. That's coming from a finite time constant in the neurons and synapses. So it answers a little bit of the earlier question that Mike asked. So it doesn't require infinite time memory in this case. So that was one example. And here's another example, which here I'm trying to compare how this full training of spiking network, how it compares with the reservoir computing, which I mentioned earlier. So in the case of reservoir computing, you only train the readout weight, and hopefully there's all the useful information in the random recurrent network already. So you fix the recurrent weight. Yeah. And I'll compare what happens when you fully train the whole network instead. So here the task is very simple. So this network receives 1 sinusoidal input, but for the output, it should be able to generate a whole different phase delayed version of the sinusoid. Yeah, so it's hard to see here, but then there's different phase represented here. So in the case of reservoir computing, if you fix the W, the network doesn't really perform too well to generate this. You can see it's kind of random fluctuation. There's no nice phase delay between the signal. And if you try to understand why, if you look at the individual synaptic activity in the neurons inside there, you can see basically this activity here is not really driven by the input sinusoid. So the neurons don't really contain good information about the input signal. Instead, if you also train W as well, you can see the first of all, the output is very nice phase delayed version of the original input. And if you also look at the individual synaptic activity of the individual neurons spike, you can see this whole range of phase are well represented in the network. So, and the individual neurons are driven by the sinusoid quite well. And it turns out you don't have to make dramatic change in the recurrent connection either. So if you can close your eyes, here it's showing the elements of individual elements of the recurrent weight before training, without training, and after training, and they look more or less the same. Here I made a plot, so you don't have to close your eyes. So here the x-axis shows the elements before training and after training, and you can see these dots line up pretty much on the diagonal. So there was some change, but not too much. And so this result shows you that even if there is subtle change in the recurrent weight, it can have a tremendous difference in how these neurons interact and create dynamics. Okay.
How many neurons?
So here, I forgot. And I think it's not too large. So only order of 40 neurons. Yeah.
And how?
And
What are your results on that number?
yeah.
40 versus 400 versus.
Oh, I didn't play with that number too much here. Here, right. Let me see.
Because it looks pretty sparse. You have about 20 rows.
Right.
Spiking.
Yeah, I think so. You can make the signal to be a lot more smoother if you had more neurons, and maybe cover a larger delay time too. Yeah.
So, okay.
Yeah.
So
So
how did you
here,
pick 40?
well, I just it was a small enough number that could do this task. Here. But also the time delay here, it's only over 100 milliseconds, which is an individual the neuron and synaptic time constant on the order of 10 milliseconds. So it's on the ratio is in the comparable scale.
But to you, does it look like you could have done it with 20?
That's an interesting question. Yeah. So, that might be because there was also a penalty term for trying to decrease the number of spikes. So yeah, maybe you're right. So it could have been done with 20 neurons too.
And also,
So,
like the time length of your signal might matter too. It's kind of like, if you look at it as like peaks and troughs, you have this diagonal peaks and troughs. We have about 4.5 cycles. So how many of those do you need? Well, you do. I mean, if you just look at the actual signal, you have 1, 2, 3, 4, and then kind of half at the beginning and the end. If you go down right below, so if you look at the top right plot,
right.
you have about 4, right?
4 delays.
4 plus, yeah.
Yeah.
Sure. And then if you go right down, that's represented right there. That's just kind of a diagonal that's propagating through the.
Right. So once you have this type of activities in the network, you can read any kind of delays as well.
Sure.
Yeah.
Well,
So.
how long of a signal did you use? So I guess I'm asking,
Yeah.
how much data do you need?
So yeah, I'm sure there will be a relationship between number of neurons and how much the delays it could create. I haven't looked into that yet. Yeah.
Like just kind of intuitively how much? Because this looks very, very strong even after the first wave. But, that's all.
Okay.
It's not too much of a question.
Okay. Well, we can discuss further if you have more questions.
Like
But yeah.
just asking about
How this works.
your intuition about
Yeah.
the time space.
Okay. Well, the next, yeah. Let's see. Well, this next task is also quite a little bit relevant. So in terms of having the spiking networks, neurons kind of develop a slow timescale dynamics. So here, so here this network is trained to perform what I call the delay memory XOR test. So here the network receives 2 input pulses. It's better if I show this. So, and the input pulse could be either positive or negative. And it has stored that information in the spiking activity within the network. And when it receives another pulse, go Q signal, then you should make the appropriate output as a function of these 2 pulses. So here is the it's exclusive OR task. So if the input had the opposite sign, then the output has to be a positive pulse. And instead, if it was 2 positive pulses, then it should make a negative output. And yeah, and it should, yeah, and you can see this network indeed performed that task quite well. And also there was a variable time gap between the pulses and also with the go queue. So it has to generalize over different time delays. And this was done using on the 80 neurons only. And so the fact that this network performed this task well means this learning rule also works in the time scale of on the behavioral time scale on the order of seconds, and which is much longer than individual neuron scale. And you can kind of see that the networks, each neurons tend to have some kind of a sustained activity, which encodes the input pulse information. So there's some neurons. So there's some of the slow time scale activity going on in here. And in fact, the same task was performed previously in another paper. And but they use the method of converting spiking neurons into rate neurons into spiking neurons. But that method required a lot larger network. It required 3,000 neurons. So this shows that if you can indeed actually optimize the spiking networks and the spiking interactions, you can have a lot more efficient solution doing the same task. Right. So in summary, so I introduced a way to differentiate spikes, and this allowed us to now apply gradient descent learning to optimize spiking networks. And this learning method indeed can optimize the spike interactions in the time scale of millisecond, as well as optimizing entire behavior in the task time scale. And now this method now gives us the top-down approach for exploring spike-based computations. And also it brings the deep learning methods a step closer to modeling the biological processes. Okay. Right, and this is just brief comparison from previous methods. So, of course, I mentioned that the spiking network was not differentiable before. So there are many papers which talks about just applying learning in just single layer. And you can't do multiple layers because there's no way to propagate the error signal because of the non-differential feature. So many papers only works in learning single layers. And there's also other papers which applies this spike time-dependent plasticity and try to see if it can be used for computation in recurrent networks and spiking networks. And even though they show some success, it turns out this method is not really general enough. And I mean, in general, it's hard to expect this local learning role between individual synapses and have some global, have the network have some desirable global effect. And indeed, many of these methods works for homogeneous random networks when the neurons are connected randomly. But if you, as long as you introduce some structures, the same learning will fail. So none of these methods are generally enough. Instead, so if you want to understand how SCDP rule is related to the computation functions, we can take the other, instead of bottom-up approach, we can take the top-down approach by calculating the gradient and see how this gradient-based learning rule can manifest as spike time-dependent plasticity. So I already showed you that how this gradient actually depends on the input and output spike times. And I think if we analyze it further for in terms of plasticity rule, we can find different SCDP rule arising as a function of what kind of task this network is performing and also a specific structure of the network. And indeed, if we look at the brain circuits in the brain, you can see different SCDP rule arising in different brain areas. And I think maybe we can get some insight for how that works from this top-down approach. So here I'm really trying to tie the levels to understand, to have a few full pictures of how the brain works. So first, this is Mars 3 levels, the computational and algorithm implementation. So this talks about what kind of problem this particular brain area is trying to solve, and the actual algorithms the system implements figures out, and how this algorithm is actually physically implemented in the neural level. And here, often people think there's two levels, the algorithm and implementation are kind of separate, but in fact, they are highly linked. So depending on what kind of hardware you have, some algorithms are more easier to implement, and some are easier, harder. And depending on depending on the actual physical neuron models we have, we can come up with different algorithms. So one can give you more algorithms more actually used in the brain than others. So by providing spiking neural models, which is a step closer to actual biology, we can hope to find and we can now hope to extract the algorithm solutions that are implemented by this network and try to understand the function in the brain. Okay. Right. Okay. So here's some a few ideas I can have, like project ideas, which can be directly relevant for some experiments. So one is what's called a fast perception task. So it turns out humans are very highly sensitive to briefly flashed images. So for example, even if it's flashed only for 10 to 30 milliseconds, and you can recognize what was in the image. And usually this duration is too short to have any rate coding to have meaning, right? So neurons at most have time for 1 or 2 spikes in this duration. And so this is it's a nice candidate case where spike time representation could be quite useful. So we can try to understand how such process happens by training a spiking neural network to perform the same task, given the same constraint on the duration and number of spikes, and see what kind of how the network processes this information. So we can discover the spike code by analyzing the high-order correlation structure in the spike times. And we can test in the experiments, see if we can look for, if we can find similar structures in the neural data. Okay? And assuming that this all works out, then we can further investigate the model to find out exactly how to perturb the defined correlation structures in the spike times, and test if the perturbation can be also applied to the animals to change the perception in the animal. So this could be more causal way to test the model prediction. Right. And yeah, and also I already showed you some of the toy models I showed you earlier could also be applied to understand how the spikes can be used to integrate information over a longer time frame. So it could be a model for understanding the evidence accumulations and in several brain areas. Right. And lastly, we can talk about some other implication of this work. So I expect this research can trigger what's called spike-based deep learning for computer science AI research. So, right. So there are two main features of how the brain is performing the computation. So one aspect is that, well, the computation is highly distributed, and another thing is it's also highly asynchronous. Okay. Both are performed by the spikes. Spikes distribute the information across of the brain areas, and each neuron can spike at any time, and that's kind of very different from how the traditional computers are performing right now. They are a lot more highly centralized. There's CPU and also global clock signal, and what we're doing in deep learning and so on is exploring the computational potential of relaxing some of the constraints. So instead of the centralized CPU, this distributed architecture in the neural networks allows us to have a lot more flexible and more efficient computations. But then we haven't really explored what happens when we also include this asynchronous aspect of the brain. So that's an unexplored area in AI that we can go further. And there are also a lot of already many chip manufacturers already being interested in it. So apparently by making the neurons to spike, we can have even higher efficiency in the processing of the AI structure. And so Intel recently came out with their own chip, Loihi, that was just 1 month ago, and IBM has their own chip and so on. And and these chips are supposedly now can process the asynchronous data coming from also the neuromorphic sensory chips. So there's silicon retina, where individual neural pixels here are making this spiking output using the event-based sampling I mentioned earlier. And of course, and this can be highly efficient because if there's redundant information, if there's no change in pixels, then you can skip the updating those pixels. So there's a lot of power efficiency saving. And you can also achieve really high sampling rate when there's a quick change in the image. So you can also even take the photos of a bullet. But it costs only like 70 microwatts. So it's highly efficient. So both this and now these neuromorphic chips are supposedly be able to handle this asynchronous data. So we have all these advanced hardwares, but so far we don't have any software to run on these chips because nobody could really figure out how to train the spiking networks. So most of the algorithms running on these chips are based on conversion technique that I mentioned earlier. So you first train deep learning network and try to emulate it using spiking neurons. But we can achieve even higher efficiency, and we can also explore if this newer computational potential in the spiking network by directly optimizing the spiking networks instead. So all this industry motivation in spiking networks are great. So this will help us further develop spike-based AI much quicker. And because this spike-based AI will be a lot more closer to actual biology, we can hope to have a lot more direct interaction between these two fields. So if you have any new findings from the neuroscience, if you can understand what's happening in the cortical microcircuit, for example, we can now directly apply it to this spike-based deep learning network and have more to replace what we have convolutional neural network architecture, and maybe you can have even better processing there. Okay. So, and also, yeah, I think this work can also lead to a more efficient brain-machine interface and neuroprosthetics by using fine control using spike times. And for example, this training method can also be applied to the retina circuits we have in the. So retina is a great system where we have lots of details of the connectivities in the circuits from connectomics data, but we also have great access to the input-output mapping. We can record from all the ganglion cells. So we can use this method to have an accurate model of the retina, and this can further allow the patients to see better using those artificial retina chips. Okay, so is that it? Yeah, I think that's all I have to say. And so long-term goal here is to really bring the AI and the neuroscience close together and have a strong, so we can facilitate advance in both fields together. Okay. So yeah. Anyway, so that's it so far. Okay. Thanks so much. Sure. Okay.
I'd like to start. Can I start?
Okay, so
Okay.
okay, so you told us a lot of stuff. Category 1 was people have tried to understand what neural networks are doing, but haven't been able to understand how to train a spike-based network.
Right.
So it's sort of conditioned on, given that you're going to commit to a spike, how might a network sparsely connected learn something useful or valuable, right? And nobody's been able to do that yet. So that's
Exactly, yeah.
we commend you on that. The second is sort of related to the idea behind event-related updates versus time-based related updates, sort of your Riemann integral versus Lebesgue integral picture that you had there, right?
Exactly, yes.
And that's interesting, too. I recall Toby Delbrook's time counter event-related retina, where he was looking at how you get a time base without a time base from a silicon retina. Okay, but so those are compliments. So now I'm going to invite you to back up a bit and address the biology. So first of all, spikes are pretty fat. They're about a millisecond wide. Some of them are neuromodulatory systems are even wider than that, 2.5 milliseconds, 3. They're kind of long.
Right.
So they've already so they use a lot of time. They consume a lot of bandwidth to begin with. A spike does. Why isn't a spike even faster? On the other hand, they also waste a lot of energy. They're the most conspicuous energetic event that a neuron does. It's literally the most conspicuous single event in terms of if you counted in ATP. Thirdly, when a neuron makes spikes, it goes out the axon. It also runs back into the dendrites. So what I'm going to invite you to do is kind of speculate about, do you see a role for the dendritic spikes? And it still seems like a slow event, despite the fact that we call them spikes and we call them events and whatnot. A millisecond is still pretty fat. Maybe it's as fat as it could get away with. Certainly for animals that use phase offsets like echolocation in any kind of animal, like a bat, that's tens of nanosecond phase shifts that those guys can detect. Certainly.
And the spikes are fatter than that.
Yeah, but the phase shifts are,
Phase shifts,
but they're
yeah.
mechanisms that sit there that are clearly sitting on neurons that are sensitive to fractions of small fractions of milliseconds.
Right.
So, so I didn't want you to take it as a criticism of the fact that you've figured out how to do gradient-based learning on spike-based networks, but to go the other way, which is why is it that after a lot of evolution, the system's still committed to doing these really energetically expensive things?
Yeah, so first of all, in terms of energy, so I guess most of the energy is used in keeping the voltage gradient between inside and outside the membrane, right? And yeah, so possibly there's so possibly the spikes are quite expensive thing to have, but maybe still there's a great trade-off for having the spikes in terms of computations. We don't know exactly what that might be. But then, in terms of the width of the spike, I don't know. Maybe what's the? Maybe it's also as fast as it could be. I don't know exactly if there's a. If you could make that spike to happen faster.
If we can do phase detection of 10 microseconds.
Right. Oh.
Some mechanism sitting there, probably a protein that can respond to that.
But maybe there's a limitation on the channel dynamics, how fast they could open and close. Not sure.
Okay,
yeah,
I was just,
but,
not really a question.
Okay, so I like your idea about spiking network in silico. It's quite interesting.
Thank
the
you.
other thing that your network reproduce a behavior level delay time, so it holds some memory inside. And then, but I have some a little bit, question about your approach to using, the deep spike-based deep learnings. Current deep learning problem is that, even people train network. It's quite difficult to interpret it, the inside structure of network. I'm talking about weight for individual connections.
That's weight, yeah.
And then, so that's why there is chance still in your approach. Your network may not do anything real. Do you have, it doesn't represent any, neuronal connectivity inside the brain. So do you have any comment?
I think there's two separate things you mentioned. One is about interpretability of the network, and the other one is how closely this network will.
Impossible. So, okay, I see. So this is just brain too complicated. So that's why we cannot start.
Oh, I haven't said that yet, but.
Can be achieved any kind of different network. So it may not be anything represented in the real connectivity. That's my question. Modeling itself is quite great. Yeah, I like it.
I'm not sure I understand the question. Are you asking, if you train these spike-based networks in the deep learning way like you've shown us, you end up with a weight matrix that's uninterpretable. Unless you sort of have something else that's roughly the same order of complexity figured out. Like you've used up capacity. Is that the question? Is that what you're asking?
Ultimately, for a solution that you should make some very high density recording all the spiking, and then that spike is happening much with your spiking network system. And then, so that is similar different network or different?
Right. So.
This is just, I just, I really not familiar with model.
Yeah. Well, so by the way, so regarding interpretability issue, of course, yeah. If you deal with large-scale network model, which is highly complicated, and then of course it will be hard to interpret this, and then there's the deep learning community are also trying to deal with that. They're coming up with new way to visualize what's happening in the network and so on. So
I think it remains to be seen
yeah.
what the intermediate layers are encoding with things like alpha. Let's take AlphaGo that plays Go. It's an active area of investigation about, given that you can train it to play this complicated game that nobody thought you could do before, what kind of structure is left over in the intermediate stages. And so in this particular case, his innovation, in my opinion, is how could you ever train anything with spikes? Why would it even commit to using spikes in the first place, and can it learn anything? I think it's early days for it. And so what the intermediate layers or what his W looks like or means kind of remains to be seen. That would be my defense of it.
So
You can pay
we know nothing about really how the spiking system can process anything. So there's a lot of even simple questions we can first try to address. Like even forgetting about this this complex pattern recognition task. If you give the, maybe we can learn more intuitively what's going on by first tackling simpler tasks, such as just basic signal processing tasks, and see how this small-scale network performs it. So first we can build an intuition and see if we build a larger network, how maybe we can understand some of these smaller building blocks for failure. Yeah. Oh yeah, so right. So yeah, so here I didn't apply the Dale's rule yet. So and right, so all the connections could be either positive or negative. Yeah, but it's pretty straightforward to impose the constraints, whether some connection has to be positive or negative. Right. Right. So I can put the constraint on which steps has to be positive and which has to be negative. So yeah, so it would be not yet. Yeah. So yeah, it'll be interesting to see how those biological constraints has what kind of implication it has on the network.
All right. Well, we're asking you kind of hard, pushing you on hard questions.
Thank you very much.